Good morning everyone, welcome to episode 1 of Maths in an Empty Classroom with me, Mr Southern. Today we'll be talking about connected particles on inclined planes. Now what I'm just going to start off with is a basic image of what it looks like so that we can talk about the forces that are acting on the system before we go on to look at an actual example. So you'll be familiar with the pulleys where you have the two masses are both hanging vertically over a pulley like so. What you may not be familiar with at this stage is if you have one of the particles on an inclined plane connected by a pulley to, by a rope I should say, to a smooth fixed pulley. Just a little bit on the language here, keywords. We've got a rough inclined plane. Rough, of course, implies that there's going to be some friction to consider, and we'll talk in a moment about which way friction is acting, and that will depend on the direction of motion of the particle. But let's begin to start off by talking about the forces acting on the particle that we can assume to be there. We have, first of all, if we look at this mass here that is on the inclined plane, we are going to have a weight component, or a weight of the particle. It's not a component, it's a weight of the particle of mass times gravity acting directly down vertically. G, of course, because this is maths, is 9.8. What I always like to do when you've got an inclined plane is, if you have a force that is acting not parallel or perpendicular to the plane, is just to draw in a dashed line like so, because what will happen is when you draw that dashed line in between the line of the force, the angle that you create there will be the angle alpha. And this is very, very useful later on when we come to look at the parallel and perpendicular components of that weight force when we look at the motion of this particle here. Right, other things that are happening, we're going to have a reaction force on this particle, on this block on there, which we'll label R, and that is acting perpendicular to the slope, so right angles to the slope. We have a number of forces acting in the string itself. We have a tension force here that's acting on this mass of 1.2 kilograms, and we have a tension force here that is of equal magnitude. It's the same size, the same number, but this tension here is acting on the pulley, whereas this tension here is acting on the block. Moving across over to this one then. This one's a little bit more straightforward because you don't have to consider angles because it's suspended vertically. So again, we have its weight acting down, which in this case will be 0.9 G. We have a tension force acting on the particle upwards, and another tension acting downwards on the pulley. Now all four of these tensions are the same magnitude, the same value, they're all the same number when we come to do our resolving later on. Now, going back to this, because the weight of this block is going directly downwards, when we come to look at the motion of this particle, because it's going to move this way on the plane, we need to consider the perpendicular and parallel components of this force. And that is why we've labelled this angle in here alpha, because if I now join up that force there to create the components into a right angled triangle, what I would have is a weight component perpendicular to the slope, which in this case would be 1.2 G cos alpha, and this one here, which is the weight component parallel to the slope, that would be 1.2 G sine alpha. And the thing that's really worth mentioning at this stage is that that is the force that people always forget. People forget to resolve, and they forget the weight component acting down the slope for this block, and that's when things start to go horribly wrong. Okay. We have friction. Now friction is interesting here because friction will depend on the direction of the particle. If the particle slides down the plane, then friction will act up the plane, because friction opposes motion or the intended direction of motion. So if the whole thing wants to slide down, friction's going to go up like this. If the whole thing wants to go up, because this one's moving downwards, then friction will go down like that. So that's a little bit of the theory of it. What we'll do in the next video is that we will apply this to an actual example. Right. So take your time to digest that and then load up the next video.